Thanks very much. So our first science highlight is going to be given by Brian Anderson, who will be speaking about AMPERE.
So some of you might know about the Iridium constellation. This is from a recent cover of JRL, which shows magnetometer perturbations. That's from one satellite, that's from another satellite, that's from another satellite. And that's observations obtained in a time span of 10 minutes. For a particular, interestingly enough, the sun is off in this direction. See, for a cover, they don't really want anything quantitative that you can make sense out of. They want something that looks really cool. And so that's what the Earth is for. This is the data. They were okay with putting the data on there, but they really like the Earth. And the sun is over here. That's a substorm onset, turns out. That's what it is. And so that's what the point of the paper is about. If I had proposed this project to study substorms, it would have been rejected before it even got to the reviewers. But anyway. It turns out that there are 70 some of these satellites, and they all carry magnetometers as part of the avionics. On this generation of Iridium satellites, it's part of the attitude control system. There are 70 satellites, so you can see the kind of coverage that you get. Now, don't be misled. If you were going to be honest about this, at any given point in time, it would be much less impressive because there would be 30 points on that screen, and what's actually happening is those points are moving through space so that you're getting a resampling of the system every 10 minutes is what's happening. Actually every 9 minutes, but we use 10-minute windows. And that's the kind of coverage that you get with that system. And we developed this, we just finished the development of this capability in May of last year, is when that was completed under NSF sponsorship. So we were able to take advantage of what was a $5 billion commercial investment, which is now profitable, and they are building the next generation of satellites, which they'll be launching in 2015. We were able to take advantage of that for a cost-benefit, cost ratio of something like, well, it's insane, so I won't even go through what the numbers were. This is a schematic of what it looks like. The satellites are in orbit. It is a communication network, so one of the data streams is this satellite actually talks to its neighbors and sends the data down as soon as a packet is closed on board. And from the time that a packet is closed on board till the time we were receiving it in our data center was, when we were operating in real time, it's about 100 seconds, no matter where the satellite is. Then there were two data rates that we used, two sampling rates. One is 20 seconds and the other is 2. That's our high rate, that's our nominal rate. And this is the system then that they process. They have to have some software processing and attitude merging and other data set preparations, and then they send the data to the AMPERE Science Data Center at Johns Hopkins. So this is kind of what it looks like. We calculate, first of all, there's a lot of processing that goes into the derivation of these vectors. Bear in mind the raw data is at about 100 times larger than that. So you're looking at signals that are on the 1% level. And there's a lot of processing and a fair number of approximations that are made. And one of the things that we need to do that Dolores Knipp pointed out, and if you look carefully, you'll notice it's a little hard to see, but where these orbits are crossing, these vectors don't necessarily agree. And that means that we have problems with our baselines. And that needs to be improved. Now, bear in mind that the attitude systems on these spacecraft only give you attitude to a tenth or 2/10 of a degree. And so that's the source of the problem right there. But nonetheless, these signals are standing out quite clearly. That's the magnetic perturbations, which we then fit with a spherical harmonic. We do not have to use any models. That is, any models for what the equatorial boundary is, or any models for what the ACE L1 measurements were. We just fit this with a resolution that's commensurate with the algorithms we have, which is about 3 degrees at this point. And then you take the curl of that, and then to get the region 1 and region 2 currents, the field line current, the Birkeland field line current system. And at our standard sampling rate of about 19.4 seconds, that's about 1.1 degrees in latitude. At high rate, there's about 0.3 degrees between samples that are sampled there. So then the question is, what can you do with this? And people have been using this. Lasse Clausen has done a series of papers on this where he takes the field line current patterns, and then he takes along a track, he then projects that data, which is shown in black, and then to that he fits a sine wave that is damped with a Gaussian. So it's basically convolution of those, just a product of those two functions. And then that's this curve. And what that does is that allows him to fit where the peak in the downward and the upward current is, and then also to locate where the interface between them is. And then he uses that to define a radius in the northern hemisphere and in the southern hemisphere. And what he noticed about that is that you see these radius increase, then decrease, and increases and decreases, increase, and then these sudden decreases. And what those were substorm onsets. So you're seeing growth phase and then recovery. And that's what he's seeing. And he's seeing this. One thing that's nice about AMPERE, and I was talking with somebody else, and they said, well, gee, it'd be really nice to see, I see that in your data. And I said, well, let's go check the other hemisphere. And he was somebody who does ground magnetometers, and he just about fell off his chair when I said, well, let's just still check the other hemisphere. I have it here. It's actually easy to do. And you can see that in the southern hemisphere, you're seeing the same dynamics. So there actually is a sense in which the data set is, you can validate it against itself, because if you're seeing the same thing in both hemispheres, you can be pretty sure it's a real system dynamics and it's not a fluke of what's going on. So that's what he saw in that. That's one thing that's really exciting that's been coming out of AMPERE, a series of papers on that. Another thing is storm-time electrodynamics, and this work initially dates back a few years when Wilder and Jeff Crowley were working on this. This is early in the April 5th, 2005 storm event at 030. I'll show you some plots on that. These are the little vectors that go into those fatal line currents that are overlaid. That's the terminator at ionospheric altitudes. And this is later in the storm. And you can see that during the storm, the signals are so large that they're way above our noise level. If you zoom out a little bit in latitude, this is what we saw before. Now you can see how expanded and intensified the system is. And as I like to say, the nice thing about AMPERE is that the auroral zone cannot expand equatorward of the system. And so that's what that was. Now what Wilder did is he took AMPERE data and added it to the sort of conventional NCAR-AMI inversions. And this is the NCAR-AMI inversion for Joule heating, not using AMPERE, but using their other sources. And then this is the distribution for the same time interval, 10-minute time interval, where he used the AMPERE data. And that's for that same left-hand time slot that I showed before. You can see that the regions moved, they changed where they were, and the intensity certainly in those regions changed. And in fact, the integrated intensity changed quite a bit. So this is indicating that there's a lot in the AMPERE data that is not showing up through the other data sets. And that's something we need to understand. It looks like we've done some runs where we take the AMPERE fatal line currents, and you don't know how large the electric field is, but you know where the large electric fields are. That's determined by where the currents are just by Ohm's law. And so there's a lot that you learn from that. So it makes a big difference. And if you want to get it right, we kind of need it. And then he took and integrated for that storm, both in the peak Joule heating, and these are the times of those two intervals I showed. You can see that without AMPERE, you're a factor of 2, factor of 3, maybe more low in terms of the peak Joule heating that you're estimating in the thermosphere. And even in the integrated sense, you can be up to several factors of low during the peak of the storm. So I would maintain that if you want to understand the ionospheric response and you're missing like 2/3 of the energy input that's at high latitude or more, it's good. You need to fix that. You need to fix that imposed boundary condition, the dynamic high latitude boundary condition, to make significant progress. So that's what Wilder was showing there, using AMPERE stuff. This is some stuff that Slava Merkin, who's at my institution, has been doing, where he took some of this data. This is for a different storm, August 3rd. And I should note that these data are the high time resolution AMPERE data, and you'll see me show a lot of that. That's really our best data. And this is the spherical harmonic fit. This is for that time interval picked in the center of that. This is the actual magnetic perturbations on the inner boundary of the LFM RCM simulation for that run. And what he's finding is that it was actually fitting in the form and the shape remarkably well for the convection pattern. Hard to see from that plot, but it actually is true. It's easier to see down here where he's got the high resolution LFM or Lyon-Fetter-Mowbray calculations, the AMPERE observations, and then the low resolution run. You can see the low resolution run doesn't get this current here and doesn't really fit things as well. When you go to high res, they're actually seeing structure that we cannot resolve in AMPERE. And so there's some compelling comparisons that can be done. And we're just getting started on that. And then this is, again, in that case, shows just before the shock arrived. There's been a southward turning. This is just after the shock arrived. And that's the signature of the arrival of the shock at the magnetosphere. And that's an intense fatal line current pair that starts here, and you see it in the simulation as well. So there's some interesting and compelling dynamics that can be sorted out using these data. So the rest of the talk is going to be on something fairly simple. Let's consider the dynamics of how we start from a quiescent state to a dynamic state, where there's no high latitude driving, and then we turn on the high latitude driving. One way that you could envision that is that you turn on the region 1 current system, and then that will lead to electric fields that are shown in red, where this is upward current and downward current on that side. And that's what the magnetic perturbations would look like for that kind of system if you were flying a satellite across here. In the mid-90s here, noon is at the top. And then as the magnetosphere responds, it forms the return convection and forms the region 2 current system so that the electric field pattern looks something like that, and then the magnetic perturbations look like that. So you could imagine that that's the sequence in which the system sets itself up. So let's find out if that's what happens. We can now do that. And this is an example which just came out. It was in that cover issue. And this is a southward turning in the interplanetary magnetic field. This has been time shifted just for advection. You can see that there's a substorm that starts off here, or at least an AE increase that starts at that time. The Ampere currents in the northern and southern hemisphere. In the northern hemisphere, you see an increase in the dayside currents that lasts until about there, and then there's an abrupt increase in the nightside currents. And you see this abrupt increase in the nightside currents as well, and perhaps this increase in the dayside currents. Well, this is what it looks like. This is the perturbations, and these are the currents that persist throughout this time. And then what happens at about some time in this 10-minute time span is this appears. And that's that perturbation that was on the cover. And that corresponds to a pair of field line currents. And then subsequently what happens is it intensifies and it spreads, and then eventually forms the complete region 1, region 2 system. Notice that these currents didn't really change, and that this is both region 1 and region 2. So that suggests that with respect to my little thought experiment, we have a problem, is that that's not what the system does. And this is fairly common, actually. We did a rough survey of about 6 months of data where we scanned for these sudden increases in the total current. Here you can see again a sudden increase in AE. That's what the nightside currents in Ampere are doing, both in the north and the south, following this southward turning of the IMF. This is what that event looks like, where you see the dayside currents here. There's the onset, and there's the expansion. And then after the expansion, about an hour later, you've got the fully formed region 1, region 2 system. So what the system seems to do really is that when you start a reconnection on the day side, you start convection, you have a set of currents that are limited somewhat on the day side, extend somewhat around to other local times. Probably the open polar cap is expanding. That is, you're adding flux to the magnetotail, the north and the southern hemisphere. Then reconnection starts in the magnetotail, and then you form this set of region 1, region 2 currents. And then as that convection closes and you close the Dungy cycle, you form the complete region 1, region 2 system. What that means is that the fringing electric fields during this growth phase and the early expansion phase are probably contributing substantially to penetration electric fields. So that instead of imposing the region 1 currents, it's really the fringing fields that we should be thinking of. And the other thing is that if you want to model the magnetosphere and the ionosphere response to imposed high latitude forcing, you probably shouldn't impose the region 1 currents and then and let that determine the electric fields and see how the system responds, because that's not what the system actually does. To do that. Okay, so let me talk about the future a little bit. We have an Iridium 2 concept, which consists of a continuation on Iridium, that is what's called Block 1 satellites. The Iridium Next satellites, these satellites, the Block 1 was first launched back in the mid-90s. Is there anyone here who wasn't alive then? I mean, it might be. That's the Block 1 satellites. They need to be replaced. The system is actually quite profitable. And there is an Iridium Next set of satellites which will be launched starting in 2015. And as they put up that replacement satellite, they'll decommission the existing satellite, is what will happen, and gradually replace the whole system starting in 2015. So the Ampere Next concept is that the Iridium Next satellites do have magnetometers. Ampere on Next could be different but superior. It's the same orbital configuration. The time sampling will be fixed, but it's actually about 2.5 times faster than the low rate sampling that we get now. So it's really, really good for what we want to do. The most important thing is that the new satellites use star cameras for attitude. They don't use magnetometers for that. So our attitude knowledge will be about 10 times better, which means we will really nail the baseline problem that we address. And so that data is going to be phenomenal. But the other thing that we've discovered that we needed to do is we need to maximize the science. And so things that we want to do are, for instance, to add community products to the Ampere website. and to improve our data processing, that is, revise the attitude estimation and improve our baselines, because that's our biggest bugaboo right now. There's also noise in the data that we need to back out and figure out how to remove. So there's a fair bit of work to do there. We also want to do higher latitude resolution inversions. The stuff I've been showing is all 3 degrees, but the data, even the low-res data, supports down to 1.2 degrees, and we need to push that boundary. And we need a faster inversion algorithm to do that. We'd also like to ingest other magnetometer data, DMSP and SWARM, if we can work out those agreements. And if you have that, and there are also regional observations you can do, because in the orbit crossing region, that's often like the orbits are all crossing in the cusp, or they're all crossing in the region where substorm onset is occurring. And so if you could do something that's not just a dumb spherical harmonic fit, but you're using finite element currents and other approximations, you could do some really cool stuff and new science in those regions. And that's what we'd like to do. And then there's multi-data type inversions, and there's going to be a lot of talk later on in the conference about that. And the other thing is to really involve the community, form a users group, have a steering committee, and have a working meeting, say a working meeting between GEM and CEDAR when the meetings are joint. Where people who are interested in this data from both communities can get together and have a workshop on that. But there's a challenge, and it has to do with the federal budgets. And the AMPERE-Do budgets, which were proposed, the proposal looked really good, and it's going to be funded, but the budgets have to be revised. One thing to note is that when the previous contract expired at the end of 2013 in May, guess what? If you don't pay for the data, you don't get it. So they've been letting the data pile up on their disk drives, but we have to pay for it in order to get it. And so the AMPERE data stops on June 1st, 2013, and we have to buy that data, okay? So we haven't purchased that data yet, but the funding is constrained. And I had to make it kind of a Sophie's choice, and my choice is to put the priority on science to make sure that the data and the products that we have, for the data that we have, are as reliable and useful as possible, as that you can do humanly possible. What that means is that AMPERE-2, as we are conceiving it now, will include only the low-rate AMPERE continuation data. There won't be any high-rate data, and there won't be any Iridium data from Iridium Next. We just can't afford it. And what we will do instead is we will work on improving the data processing and products we have, and then the AMPERE data we get will begin to degrade starting in 2015 or so as the next Iridium launches occur. But there's an awful lot of science that we can do with that data. I mean, it's really cool stuff. So that's where I want to close. Thank you very much.